Good evening and welcome to the third season of Scientifically Speaking, an interactive online lecture series that connects world-renowned scientists to high school students and teachers. Carefully curated to inspire, excite, and ignite young minds in the field of scientific research, this interdisciplinary lecture series aims to help students develop a creative way of looking at life and connect their learnings to address real-world problems. Our speaker for the lecture today is Professor Mahan M.J., Professor of Mathematics at TIFR, Mumbai. The moderator for this session, we have Ms. Aisha Saluja, who is the IGCSE HOD of Maths at Jayashree Periwal International School, Jaipur, and also teaches Maths to IBDP students in grades 11 and 12. Ms. Saluja did her B.Ed from the renowned Guru Gobind Singh University in New Delhi after completing a BSc in Maths from Delhi University. Not limiting herself to just one subject, she has also pursued an MA in Economics from Rajasthan University. Ms. Saluja has been associated with Jayashree Periwal International School, one of the leading IB schools in the country for more than a decade. Now, in all, she has more than 15 years of teaching experience in the field of mathematics. Moreover, Aisha is also the coordinator of the coveted Stanford University Exchange Program at Jayashree Periwal International School. A very warm welcome to you, Aisha, and kindly take it from here and introduce our speaker for the day.
Thank you, Parneet. A very good evening to everyone. Welcome to the third season of Scientifically Speaking. My heartfelt gratitude to Ashoka University for organizing these lectures, which actually bridge the gap between experts from these different fields and the high school students and teachers. It is my honor to introduce today's keynote speaker, Professor Mahan Maharaj MJ. Having earned his PhD from the University of California, Berkeley, he worked as a professor of mathematics and dean of research at the Ramakrishna Mission Vivekananda University till 2015. Presently, he is a professor of mathematics at the Tata Institute of Fundamental Research, Mumbai. Just like his name, his work in the field of mathematics, namely the area of hyperbolic manifolds and the proof of existence of Cannon-Thurston maps, is magnificent. He is a recipient of the 2011 Shanti Swarup Bhatnagar Award and the 2015 Infosys Prize for his contribution towards mathematical sciences. Today, Professor Mahan will enlighten us on the topic. Almost all shapes that we see around in space are examples of surfaces. He will describe the method of dating back to the 19th century of understanding these and also describe more sophisticated geometric structures on surfaces. So without any further wait, let's hear it from the monk who really knows his mathematics. Over to you, Professor Mahan.
Thanks a lot, Aisha. Very kind of you to give this introduction, and it's a real pleasure. Real pleasure to be at least virtually in Ashoka, because there are very fond memories of my trips to Ashoka a couple of times, and it's like sort of seeing a child grow. I mean, it's an institute growing organically, and it's academically. I mean, it's basically you go in there and you sense the academic vitality of the place. It's a real pleasure. Okay, so let me thank you very much, and let me just share the screen. Yeah. So is this visible?
Yes, Professor, it is.
Okay, great. Thanks. Okay, so I'll be talking about shapes and geometry of surfaces. What does that mean? So in very grandiose terms, I mean, what does science do? It fixes a window to nature, and then through that window, whatever information you get is categorized. So in this particular case, that metaphor is almost literal, because what we are after is no less than essentially taking our entire visual information at a naive level and trying to classify all that. So what's the point? So if we look around us, so we have this bewildering multitude of shapes that we see. So this is a globe, and this is something more exotic, and something, well, that perhaps that same exotic thing is a couple of balls with some rubbery stuff in between, which you start stretching. And who knows what these shapes are? I mean, we don't even give them names, but these are things that we see around us. So, and this is something even fancier. This is supposed to be, I mean, essentially this golden little pipe that you see winding around in space it's what's called a knot. So essentially, you take a string, well, a thickened string, and you've tied it up and you pasted the two ends together in space. So that's what we call a knot. And then there is some kind of a surface spanning it. So anyway, I mean, the specifics of this is the specifics are not important. What this is supposed to give you a feel for. Again, let's sort of go back and forth a couple of times. So when we see, I mean, it's from fairly simple shapes like the surface of a globe to these pretty exotic shapes. This is what we see around us. I mean, this is the range of things that we see around us when we look around. So let's now try to sort of go from these very, very general terms to slightly more specific notions. What do you really see? I mean, when you're looking at, say, something, so you're sitting somewhere and you say, look at a chair. Do you really see the three-dimensional chair, or do you infer the third dimension in terms of your sight? So there's this notion of three dimensions. Actually, it's because of this binocular vision that we have, and what we really see is the surface of the chair. So if you imagine yourself to be a little, I mean, so sort of coming closer and closer to the surface of the chair, and when your eye is almost on the chair, you're just going to see a little patch of land, yeah, a little patch of the chair. So this is, I mean, so when you're looking at something, what you're really seeing, what is the information that is being conveyed to the brain is just the surface information, not, so you can't sort of see some point that's located inside the wood of the chair. Yeah, you can't see, suppose there's a pin hidden inside the chair, you can't see it. You can only see the surface. So we were supposed to be talking about shapes and geometry of surfaces. And what have I said so far? I have said basically a tautology. Surfaces are surfaces, nothing more, nothing less. Okay? But now let's try to make that tautology a little more significant, a little richer in content. And in order to do that, we are basically asking the question when we say that, look, you take all your visual information and try to organize it. What are we asking for? We are asking for a framework of knowledge which will take all this visual information and put it into convenient dockets. Yeah? So essentially, let's say when you come across numbers, what do? What is the number one? What is the number two? These are actually convenient dockets. So for example, nobody has seen the number one. One can see one chair, one fan, one person, one apple. But what about the number one? It is the common abstraction, the thing that is common between one chair, one table, one fan, one apple is the number one. This is what in mathematics it's called an equivalence class. So, but this capacity for the human brain to abstract out and find some unifying theme between various notions in a pretty precise sense is what gives rise to mathematics. So when we are asking for a classification, for a way of understanding all visual information, what we are really asking for is a way to abstract out take this entire visual information and start constructing on it or start abstracting from it enough features to put it into convenient dockets. So how are we going to organize all this information? What we need is a formal structure. In order to get a formal structure, we'll have to give a more precise notion of what a surface is, more precise than all visual information. That is much too loose. So this is what I was hinting at. So let's try to get at a more precise notion of what we mean when we say that when you look at a chair, you're really looking at the surface of the chair. What does that statement really mean? It's trying to excavate, it's trying to get into the meaning of that statement and get at something that's something very precise, something that can be manipulated formally. So what are surfaces? So again, let's pose that question that we started off with again. But now we've already gotten a certain superficial level of understanding. We want a deeper, more precise, more technical understanding. And as I said, when you look at a chair, if you try to move your eye very close to the surface of a chair, what you're going to see is just a little patch of the chair. Imagine yourself to be an ant, where the eye does not look too far, it does not see as much of the world as we do. And allow it to move on the surface of the chair. What will it see? It's just going to see a flat surface, right? A flat two-dimensional surface. Forget ants now. Think of ancestors of us, human ancestors. For a long time, we thought that the earth was flat. We did not have any idea of the global shape of the earth. So if you look at the Arabian Sea and Bombay just behind me on my virtual background, the surface of the water, it looks like a flat sheet of water, right? So so even human beings, when we look at the surface of the earth, we think the surface is some two-dimensional object. It's only when people look at the earth from space that they realize, oh, I see, this is actually not just something flat, it's something round. Okay. But what is the upshot of this discussion? It means that once you zoom in very close, then what you're going to be looking at are things which locally just means after you've zoomed in a lot, it looks two-dimensional. Yeah. So very close up, it looks two-dimensional. This is the principle behind the construction of maps and atlases. What do people do? They take a patch of land and then they draw the topography, and that is projected on a flat sheet of paper. Whatever is there on the flat sheet of paper is actually supposed to denote a part of the earth. So the surface of the earth is an example of something that is locally two-dimensional and technically, not just in terms of loose terminology, even in terms of even in terms of precise terminology, that's also an example of a surface. And now what is the problem that we are trying to address? We want to understand all locally two-dimensional objects. What did we start off with? We started off by saying we want to classify all visual information. That sounded very grandiose, but we wanted to make it more precise. So then we wanted to look at surfaces of objects. Became a little more physical. Now we are coming to something where the language is even more precise. We want to understand locally two-dimensional objects. Now, what does understand mean? Typically, when we say we understand, we actually have a classification scheme in mind. So, the objects that we have to understand, locally two-dimensional objects, reasonably well nailed down now. But when we say we want to understand, and when we say we want to classify these things, what do we really mean? In other words, what is the framework in terms of which we are wanting to understand? In other words, what does the word understand even mean? So we wanted to understand something. The something we've nailed down, surfaces, two-dimensional objects, locally two-dimensional objects. But what is it? What is the framework in terms of which we want to understand? That needs to be spelled out. What we want is an exhaustive list. Yeah. So this list means every place in that list marks out a docket. And what do we want to do with that? It's like a folder in a computer or in a laptop. It's basically going to be a folder. All things which are similar which contain the label. So contain the label on the folder will be put into that folder. So for example, you can classify number of objects. Yeah. So if you have one apple, you're going to put it in the docket 1. 2 apples, put it in the docket 2. 3 chairs, put it in the docket 3. 3 chairs, 3 tables, 3 people, all of that is going to be put in the docket 3. Yeah. That's what we want. So we want a similar kind of an exhaustive list. Yeah. Which means exhaustive list means what? Any surface that you see, any locally two-dimensional object that you see is going, there is going to be a docket inside which you can put it. That's what exhaustive means. Next, there should be no redundant elements. So if you're given an object, there should be exactly one docket in which you can insert it. The first says there is some docket, and the second condition basically says you can't put it in 2 different dockets. Yeah. So this is the first thing that we want. This is the kind of list that we want. And given one of our objects, given one of our locally two-dimensional objects, we want to say which point in the list it belongs to, which docket in the list it belongs to. Then we'll be able to say, basically, you see an animal around you, you say, okay, this is a dog, this is a cat, this is etc., etc. What have you done? You've taken that animal, abstracted out some features. Now you have a docket in your head called dog. So that's the docket in which you have put. We want to do the same thing here with surfaces. So implicitly, we want to basically say that this guy belongs to some particular docket, which means we also effectively need a way of saying, given a surface, there is one surface that one surface say in the docket 2. Yeah. And then we'll say, okay, you've given me a surface, this belongs to that if the surface in docket 2 and this new surface that we have now are essentially the same. So there has to be, behind all this stuff, a way of saying when 2 of these guys are the same. Yeah. Which means we'll really need to spell out what same means. For example, you could see a dog which is just a small dog. Again, you see a big, say, Alsatian. And then, but you still say, oh, these are both dogs. Yeah? But somehow or the other, that means that some features have been abstracted out which allow you to say that both an Alsatian and a Dachshund are actually dogs. Yeah? So we need something like this. So we need a way of saying when these 2 fellows belong to the same species, same genus. We want to do that now to surfaces. Good. So I think that we've now spelled out what the problem is. Now let's go back to the problem. And we said that a surface is something that is locally two-dimensional. And we talked about maps. Here is a picture of the Earth. So a globe, let's say. If you look at these little rectangular patches there, yeah, what does that look like? It looks like a little square rectangular piece of paper. That's what is taken out and various stuff drawn on it, and that's what appears in your atlas, in your geography books, right? So once you zoom in into one of those little rectangles, the surface of the Earth looks locally two-dimensional. Here's something which apparently has a very different kind of shape. Namely, this is some rabbit, let's say made out of some kind of a balloon. Yeah. And you see this little square on the right. What has happened? What has happened is that you've taken a little square patch on the body of this rabbit, and then you've pasted it. So that means the surface of the rabbit also looks like a two-dimensional piece of paper. Exactly like the previous diagram, the globe is a locally two-dimensional object, so is the surface of this rabbit. So the surface of the rabbit and the surface of the globe, 2 objects of hugely different sizes, are examples of surfaces. Fine. So now let's give even more precise definitions. you're not really expected to follow it. I'm just giving it for completeness, and then I'll spell out what it means. So a surface, now we'll have to give fairly abstract definitions, but I'll say what this is. A surface, mathematicians have a name for these. These guys are called two manifolds. Don't be intimidated by that. It's just a name. It's a space. Forget that word topological there. What property does it have? Basically, it means that around every point you'll be able to draw a little graph, yeah, chart paper, and you'll be able to put coordinates, x coordinate and y coordinate. That notion has a technical name. It basically means that every little point has a little patch around it, which you'll be able to put down on your graph paper in your notebook. That's the meaning of this expression, locally homeomorphic to R2. You don't need to know the terms. You don't need to understand these precise words. I'm telling you what it means. It means that every point has a little chart around it, which you can actually replicate on your notebook in a graph paper. And we have seen examples of things which actually, when you blow it up, it becomes nice, round, like a sphere, like a globe. Are there other examples? And the answer is, of course, there are other examples. So here is another example. This mathematicians call a torus. It's actually, I mean, you see this kind of thing. This is the surface of a donut or the surface of a bicycle tube. Yeah. So this is another example. But this guy and the sphere are not the same. Why? Because the sphere does not have a hole inside it. This torus definitely has a hole inside it. But if you look at it closely, if you look at it very, very sort of at a small distance, what are you going to see? You're going to see these little squares that comprise it. Yeah. So even on the surface of the torus, if the Earth we lived on was actually in the shape of a torus, we'd still be able to construct maps, just as we construct maps for the spherical Earth. Good. Now, we wanted to go back to the problem of classification. I've sort of given now again a rehash of what surfaces mean. But now we'll have to go back to our problem and ask, what was the problem that we were trying to address? The problem that we were trying to address is a scheme of understanding all visual information, which at this stage means a way of classifying all surfaces. Again, we've nailed down in terms of a precise definition what a surface is. Now we need a method of saying when are the same. So using the word same in different senses is going to create very, very huge amount of confusion. So that's why mathematicians use different terms for using the word they are same, but in different contexts. So here we use the word homeomorphic. Yeah. Two surfaces are homeomorphic, which means same in a particular context. The context, it's a
It seems there is an internet issue with Dr. Mahan. We are going to try and get in touch with him and resolve this. If you guys have any questions with what has happened so far or whatever he's talked about, it would be great if you could type your questions in the Q&A box.
Yeah, I'm sorry. Actually, I think I just lost connection for a while.
Hi, Dr. Man. Good to
Yeah,
have you
hi.
back.
Sorry. Yeah, I lost connection for some reason. I have no idea why. Let me
No
just,
problem.
yeah. Yeah, okay. Yes, this is fine, visible.
Absolutely, it's visible.
Hello? Yeah, great, terrific. Okay, so yeah, so we were actually at that stage where we had basically said that the kinds of objects that we are trying to classify are surfaces, and we really wanted to have an understanding of what understand really means here. And we basically reduced it to a scheme of saying when two surfaces are the same. And here is the word for it. Basically, there is what we call a homeomorphism between them. What's a homeomorphism? It's a continuous map from one space to the other with a continuous inverse, which automatically implies that in terms of as sets, there's a bijective, there's a one-to-one correspondence. Every point in the first one goes to a unique point in the other, and every point in the second one comes back to a unique point in the first. That's what it means. And what does continuous mean? It means there's no tearing and gluing. So the intuitive idea is that the first surface can be continuously deformed to the second surface without tearing and without gluing. What are examples? Here is, yeah, so this is a dumbbell which cannot be used for exercising. Yeah, so there's this fat stuff in the middle. So you start off with this dumbbell with three bells. Yeah, and then you essentially what you're doing here is you're outwards, and then the middle part becomes narrower, and the two ends become thickened, and then once you've sort of flowed it all around, all down, you finally boil it down to a round spherical object. I mean, this is something that's the one at the bottom is sort of almost round and spherical. You could blow it up and you got back your sphere. So what we are saying is that in this way of understanding things, the detailed shape does not matter, but if you can continuously deform one to the other without tearing and without gluing, then the two are the same. So the stuff that you started off with first and the stuff you're ending up with are the same. Okay, good. So here's another example. So you started off with something that looks like a very carunculated lemon, and then you, oh boy, keeping on saying that my internet connection is unstable. Okay, let's try our luck. Okay, so you've started off with uh, a rock-like, I mean, a lemon which has a lot of wrinkles on it, and then you started smoothing it out, and you ended up at this nice round smooth lemon. Okay, this is also an example of a sphere, and so now we want to solve the problem of classification. So let me just give you three examples which look very different. So this is three, it's essentially like a pretzel, but with now three rings in it. Yeah. And now in the second one, all those rings are actually arranged along a line. And here it's like a teapot with three handles. Yeah. You can't quite drink tea out of this, but it's around. But it's like a round ball. Once you flatten it, where do you go and make it maybe a little smaller? You come back to the first picture. So the first picture can be obtained from the last picture by continuously deforming it. And if you run the deformation backwards, you're going to go from the first picture to the second picture. Now you stretch this one, take these two ears, yeah? It's like a fidget spinner, right? So you suppose it's made of plasticine, you stretch it out and then slide this extra handle on the right side into the middle, and you're going to get this picture on the second slide. So what's happening is that all these three objects can be obtained from each other by deformation. So they are homeomorphic. Yeah. And what's happening then? Essentially, it means that there are these numbers of handles. And that seems to be what's common is essentially these numbers of handles. And that's not a coincidence. And this is really, I mean, we'll end with this classification theorem. There is one word which I'll use, and maybe I'll say a little bit about what that word means. Suppose you have surfaces, but you put a little bit of adjective on it. It's a closed surface. Closed surface means that it occupies a bounded amount of space in 3 dimensions. Yeah, that's what a closed surface is. There's another adjective, orientability, which I have used here. And essentially, we had started off by trying to understand what
I'm so sorry, Professor Mahan, but
all
I
dimensional
think
surfaces are, what all visual information is, into some kind of a classification theorem. Yeah.
I think there is a little bit of an internet issue. Maybe it will help if you switch
Yeah.
off your video.
Okay, fine. Yeah. Is it better? Is the audio better?
Yes, yes, at the moment it is.
Okay, very good. So we wanted to do a classification of, I think, I mean, am I still audible? Can you just respond? I mean, I think I just lost the side panel.
Absolutely, absolutely.
Oh, great.
You're audible.
Terrific, terrific. Okay, very good. So here's the thing. So we were wanting to classify all visual information. We reduced that to the classification of surfaces. And now we've made the statement the question much more precise. What is the classification for all closed orientable surfaces? So I have not told you what orientability means, but I'll just say that in a little while. Closed just means it occupies a bounded amount of space. How much, how large, doesn't matter, but it doesn't go on infinitely. Yeah. So a bounded surface is homeomorphic to a sphere with n handles for some non-negative integer n, which means what? The dockets are actually, we started off by saying classify things according to numbers. So that's just not whimsy. This is a theorem that we had in mind. Really, if you look at 0 and then 1, 2, 3, 4, 5, 6, 7, 8, etc., and you mark your dockets, your folders by just these numbers. The first docket is marked 0. The second docket is marked 1. Third is marked 2, etc., etc. Then the previous picture, this guy is going to come in the docket 3. The sphere that we started off with, the rabbit that we had, all that comes in the docket 0. The donut or the surface of a bicycle tube, that comes in the docket 1. And the theorem basically tells you, you take any of these closed surfaces, bounded surfaces, one extra little condition which I'll say a little bit about, and then stop. Any closed surface with this extra little subtlety about orientability fits into exactly one of these dockets. So you can set up, basically, once you see that surface, you unwind it a little bit and then assign a number between 0 and some, you can assign either 0 or some positive integer, and that gives you a complete classification theorem. So we started off with an ambition of classifying or understanding all the visual information, and it boils down to this theorem, which basically says that yes, this problem can be solved provided you're looking at things which are not too wild. They occupy a bounded amount of space and they are orientable. So what does orientable mean? It means it has well-defined sides. So this is a painting of Escher, which is something that is non-orientable. So there's this ant crawling on this object, which is what is called a Mobius strip. And if you look at its, look at the middle leg, it's like a little normal direction. That means it's pointing out of the surface on one side. But if you follow the ant, you come back to an ant just below the previous ant, and then that normal direction is pointing in the opposite side. Yeah. So the same object, once you pass through through a path, you're going to have essentially the two sides that we see locally are not actually two different sides, they are the same side. That's what this picture is telling you. Here is another example which is a little more exotic. I won't say what this is. It's basically what's called a Klein bottle. This is another example of a Klein bottle. Okay, so this was supposed to be at something examples of things which are non-orientable. So what is orientable? Let's go back to that statement. It has well-defined sides. So you can't start on one side, take a path, and then come back to the opposite side on the point where you started. With this little extra subtlety, the problem that we started off with, classify all visual information, does have a solution. You look at all closed orientable surfaces, you can bring them into bijective correspondence with dockets labeled 0, 1, 2, 3, 4, 5, 789, etc., etc. So essentially, all these surfaces are determined by one number, which is what? It's the number of handles on this solid teapot. Okay? That is the classification theorem. So let me stop there. Thank you very much for your attention.
Thank you so much, Professor Mahan. I'm sure we all have learned so much, and there is so much more to learn. I'm definitely sure that, I became more conscious about the complexity of each shape around us. And I do understand that usually mathematically you try to simplify and classify each object. It was very interesting how you broke down a complex topic into probably smaller branches and connected it to what we see every day. And I'm sure there are a lot of questions brewing in the minds of our young audience. So just let's dive straight into the question answer session.
Yeah. Thanks, Aisha.
So one of the questions that I have, I think it's a two-part question. It says, can the height of an object be 0? And is it possible to see two-dimensional objects in the real world?
So the answer to that is, by the way, Aisha, when you mentioned, do you have the name of the questioner along with that? That would be good.
Yes, I think I can.
Never mind, it's not important. It's not. Yeah, okay, very good. So the answer to that question is both yes and no. So here is the thing. I mean, if you're looking at the surface of an object, you're really looking at only the surface, which means you're really looking at height 0. You're not looking at something. I mean, your eye is just seeing only the surface. Yeah? It's not seeing something further in. Yeah? It's not seeing the depth, which means when you watch, you always watch height 0 things locally. On the other hand, when you're thinking of yourself, this is when you're saying that this is the only information that I'm interested in. So whenever we address these questions, we really have to unravel the question and basically ask you, what really do you mean? Yeah. And when you're looking, if you think that you're really looking at only the surface, then yes, then you're always looking at height 0 objects. If on the other hand, you want to say whether an idealized height 0 object actually exists physically, the answer to that question is no. So if you are asking the question from a mathematical point of view, the answer is always. If you're asking the question from the point of view of physics, then the answer is never. Okay?
Wow, that is interesting. So another question that we have is, the geometry of surfaces in temples is unbelievable. So how do you think that how our ancestors have come up with this without advanced technology? How did they come up with these? The geometry of the temples.
See, the thing is, here is the question. I mean, the geometry of temples is just one example. Yeah. So there are two things here. One is, when did geometry, let's say, when did geometry start as a formal subject? Historically, if you go back to Euclid, that's 200 BC. Yeah. That's a bunch of years back, right? And the way we sort of study geometry today in schools, this axiomatic method, that really goes back to the Greeks. Yeah, that's one aspect of it. The other thing that you're talking about, geometry in India, that history, say for example, what the kind of things that these people were interested in, it came from fairly precise astronomical calculations. Yeah. So understanding, see, essentially, even till 1500s, mid 1500s, science was not divided up into this is physics, this is mathematics, this is chemistry, this is biology, etc., etc. All of it was called natural philosophy, philosophy of nature, trying to understand nature. Yeah. What has happened is that our brains are too small to contain this explosion of information, so we divide it into subjects. Yeah. So at that time, natural sciences, particularly astronomy, shapes of, I mean, how planets move, etc., etc., people wanted to understand those things. Yeah. And those things were actually translated into various schematic diagrams, which they drew either in stone in India or on the sand in Greece, etc. I mean, there are various, I mean, the particular medium is not important. But this urge to understand the universe that we are in is something that's universal. Yeah. And then it fills you with awe. Yeah? And an expression of this awe is found across cultures. And one of those specific expressions of awe is temple architecture. You go to Greece, you'll see a different kind of an expression of that awe. And what is behind all of that? It's the fact that we look at these shapes in the world, on this earth, and we try to abstract it out and make it precise. And that particular paradigm of understanding shapes is what is reflected in particular in the temple architecture.
Right, absolutely. I mean, the way we can see mathematics is everywhere. It's even if the things
absolutely.
that we don't imagine it in, it is there as well.
So for example, shapes of life, forget temples. Temples, I mean, human beings are a very, very young species. I mean, we are just, 5,000 years old in terms of all these settlements and temples. Flowers have been around for millions of years before that. You look at the shapes that have been, that they go around, that's geometry. I mean, that's the shapes of flowers, they go, if one starts excavating, one starts trying to understand, there are incredibly intricate and deep mathematical patterns hidden in the way flowers are shaped, in the way leaves are shaped, and so on. In the way trees, I mean, you look around us, I mean, trees have been around before any animal came on the earth. I mean, if they hadn't generated oxygen, all us oxygen consumers would not have arrived. All of that was there. I mean, and all of it provides us geometry. All of it provides us with the shape. Oh, I forgot to say one thing. The study of shapes via this homeomorphism, it has a name. It's called topology. That's the name of the subject.
Perfect. I mean, I can see that you clearly love the geometry in nature, because I saw the picture of a rabbit, and I know you've given an example of the flowers and the trees. Just out of curiosity, how did this interest begin? Like, what was was it like a process that developed over a period of time, or was it like one instant you?
Of course. It develops over time. I think so I guess in school, one likes, I used to like geometry most, because I think, so people are, I think there are people who are visually oriented, and for them, it's visual information. We have really human beings have two powerful senses by which we process information. One is using the eyes, one is using the ears. Yeah. So those who like to see and understand things visually, geometry is a very natural thing to be attracted to.
So we have another question which says, what type of surfaces are not closed surfaces?
Excellent. So here is a very simple example. Say, suppose you take a piece of paper and you fold it up, just a cup, and assume that cup is actually, it has no thickness, then what is happening is that there is a rim. Yeah, it's not closed. It's not closing up on itself. Yeah? If you look at, or maybe even simpler is just a round piece of filter paper, so a round disc. Yeah, a disc which has an edge. Something which has an edge is not something which is closed. Yeah? But if you look at if you look at, so this means this ties up with the first question. If you think of that disk as something that has zero thickness, then it has a one-dimensional edge. It has a circle on the boundary. Yeah, that edge being there is something that violates closeness.
We have
But if you
another
take
question.
two such disks and cap them together, then it becomes closed. Yeah, then it becomes a round sphere. Basically, you have the lower hemisphere, you have the upper hemisphere, and you put them together, and you get a sphere.
Absolutely. And it also says the object is allowed to be solid or hollow, or only solid. If hollow, then is it possible that homomorphism exists on one side of the shape, not the opposite side?
Sure. So here's an example. I had shown you a picture of this bicycle tube, right? Yes?
Right.
So imagine that bicycle tube is not just a hollow bicycle tube, but you put in some plasticine inside. It's some solid bicycle tube, yeah? And now you draw, basically what you do is from inside that bicycle tube, suppose there's a bubble inside. So assume that this is something transparent so you can see what is going on inside. And suppose you can remove from inside that bicycle tube, you can remove a little, so it's plasticine. You can remove a little bubble of a little solid ball of plasticine from inside. Or you can also remove another torus, another solid torus. So basically take the solid rubber tube that you have and make it a little thick. Yeah. Then the inside is going to be another torus, or it could be a sphere. So on one side you'll have two tori. On the other side you could have either a torus or a sphere. What basically one is saying is that there are two things. You take this solid rubber tube, make that rubber boundary thick. That basically gives you a channel inside, and outside, of course, it is like a torus. Or you could fill the whole thing with solid rubber and then take out a little ball. Outside it's a torus, inside it's either a sphere or a torus. So certainly it is possible.
And is there any classification of the non-orientable surfaces as
well? Yes, there is. So there's a complete classification there also, and essentially you bring it into bijective correspondence with, again, positive integers. So there's this picture that we had drawn of a Mobius band. That's an example of a surface with boundary. Yeah? I mean, it's not an example of a closed surface. There's an edge. Yeah. But if you take two of these, I mean, what it turns out is that the edge is actually a circle. Yeah. It's a circle which wraps twice around in space. If you look at study that picture of the Mobius band little carefully, that's what you'll see. You start spiraling around, and then you spiral back again. These are sort of at the basis of many pictures which are apparently communicative of illusions by Maurice Escher. Anyway, yeah. So that Mobius band is really the building block of all closed non-orientable surfaces. Yeah.
And how can one measure the angle of a triangle on a non-Euclidean space?
I did not come to that today. So what does one mean by, what exactly does one even mean by non-Euclidean space? Yeah, one will have to spell that question out. Essentially, it means that the Euclidean geometry, what we study in school, is based on what we call this parallel postulate. Given a straight line, given a point outside it, there is one and only one straight line through that point parallel to the base one. Yeah, that's an axiom. This is called Euclid's, it's called the fifth postulate, or the parallel postulate. That can be violated. You could have a geometry where Given a straight line, this is an example that when you be given fast. Given a straight line, given a point outside it, there does not exist any line parallel to the first line through this new point. Is that geometry replicated in something we know? Indeed it is. What is a straight line? It's the shortest distance between 2 points. So now look at the surface of the earth. You take a point on the surface of the earth, say Mumbai, and you want to fly to London. Yeah. What does the plane do? It takes essentially the shortest path. That's called a great circle. Yeah. What's a great circle? Essentially, you look at a plane which cuts through the earth and passes through the center of the earth. It's going to cut the surface of the earth in a circle. Those circles are called great circles. Those are the straight lines on the shortest paths on the surface of the earth. Yeah. And now let's say basically the angle between one of the longitudes and say the equator. What is the angle? The angle is 90 degrees. So what you have to do is you have to look at it very locally on a short scale and then look at a little germ of a line that is going up to the North Pole, a little germ of a line that is going along the equator, and there it's almost like a Euclidean setup. And then you measure the angle there, that's 90 degrees. That's how you do it. This is the most general thing. I mean, you can do it on the surface of the earth, but this is really the most general way of measuring angles. Looking at it very close and then measuring the angle. Okay. Reducing it to the Euclidean situation, so to speak. Yeah.
We have another question which says, does it mean that anything which is not spherical is not closed?
No, that's not true. The torus that we gave an example of, that's an example of something that is closed. What does that theorem say? The classification theorem says that any closed orientable guide is a sphere with some n handles attached to it. It's not a sphere. The sphere is a sphere with 0 handles attached to it. It could be 1 handle, it could be 2 handles, it could be 3 handles. In particular, it could be the torus.
And do we have the ability to view the non-orientable objects, or do we only have the vision and the brain capacity to view orientable objects in real life?
I showed you a picture of the Mobius.
That was a very interesting bottle.
Yeah, so you definitely, all of you have the capacity to see something that is non-orientable.
Absolutely. And till high school, we are taught that the carbon has 4 valences. I don't know if it sticks to your topic or not, but under special conditions, it can form 5 bonds. Likewise, is it possible to have more than 3-dimensional, like 4D, 5D?
Oh, of course. Yeah? That the answer is yes.
Yes, then why don't we see such objects?
Yeah, this is one of the tragedies of being a member of this species called Homo sapiens. I mean, that's all. So, yeah, I mean, it's just that we can't see more than, I mean, so there is I'm giving you a sort of a frivolous answer, but essentially, I mean, there's a deeper question behind this. Now, what's the deeper question? Why is space 3-dimensional? Why is time 1-dimensional? That essentially is asking some foundational questions about physics. Yeah. I don't think we really have a satisfactory answer to this deeper question yet.
Maybe we'll need more time for this.
Yeah, well, essentially, I mean, there are things which, there are theories in physics which basically talk about emergent space-time. This is going to be very far from my topic. But essentially, what given the kind of ways of understanding that we have with us today, what is the kind of space-time that we can grasp? And essentially, the answer has to give you that 3 space and 1 time is the answer.
Is the only way.
Yeah.
Absolutely. So, Professor Mahan, is there any application of topology which we can link to maybe human anatomy or AI? I mean, I saw a picture of a rabbit, so it just
absolutely.
And what could those be?
So here is one. I mean, let's take topology and go a little further with that. So essentially, look at specific shapes. So then it becomes. I mean, this is what we talked about. Topology is essentially. So for example, There are these objects which have come up over the last 10 years in physics called topological insulators. So basically, everybody knows that insulators are useful, right? I mean, and otherwise you'd get an electric shock. But what would be an insulation of some phenomenon by merely the topology, by merely the shape? This is a theory that has been coming up over the last decade in physics. And yeah, so topological insulators, semiconductors. I mean, there are things which are just coming up right now, I mean, over the last decade, etc., etc. But even, so in terms of human anatomy, here is a problem that I would like to sort of throw before the audience and before we stop. So the surface of the human brain, yeah. What's happened is that it's highly wavy, right? I mean, there are these gyri and sulci, right? So there are these ups and there are these downs, yeah, the crest, etc., etc. Why? Why isn't a nice smooth round ball? Why? Question one. Question two. If you look at a tree, what's happening is that the branches are dividing, and then the surface of the tree is like, again, something very similar to the surface of the brain. I mean, it's something like the foliage has, I mean, it's become like little very fragmented, and there's the foliage on top. The human lungs, yeah, what is it doing? It's essentially, I mean, the surface is extremely wrinkled, yeah. Why is all this happening? What is the physical problem that all of these guys are trying to solve? The human brain is trying to multiply its connections maximally, one. The tree is trying to increase its surface area most so that it can get the most sunlight. The human lungs is trying to maximize its surface area most so that it can get the most amount of oxygen. And these very similar shapes in very different biological situations arise whenever a system tries to maximize surface area. If you minimize surface area, then it's going to be, say, basically when water falls by surface tension, it becomes a round sphere. What is it trying to do? It's trying to minimize surface area. But here are natural systems, biological systems, which are trying to solve a problem of maximization of surface area. That gives rise to a particular kind of geometry, a particular kind of surface, yeah. And that's something that does come up, and it's only now with the understanding of a particular kind of non-Euclidean geometry, it's called hyperbolic geometry, which would take us very far afield, that we are able to, that we are beginning to understand some of the mathematics behind these phenomena. Okay, yeah. Yeah.
We
are almost
done. Yeah, we're almost done. I'll just take one last question.
Yeah.
Is our space-time fabric an orientable surface, or can black hole be thought of as holes in our space-time manifold?
So here's the thing. See, again, this is a question that actually conflates the mathematical way of thinking about it and the physical way of thinking about it. Yeah, that's not a good idea. If you're thinking about it physically, then beyond the surface of the black hole, space-time ceases to exist, because you're not going to get any information out of it. So whatever is happening inside is just speculation, right? On the other hand, if you're saying how does a particular amount of mass in space-time evolve, and you're just going to write down the mathematical structure of it, then the black hole is part of that space. So the second is a mathematical way of looking at it. The first is a physical way of looking at it. It depends on what lens you use to view what we call reality.
I think we can go on and on this topic. I think there are so many questions, more and more questions that are flowing in. But I think we are a little short on time, so we're going to stop right here. I mean, today's lecture was really an eye-opener because I hope everybody realized that there's so much more to mathematics than just textbooks. And your lecture today just proved that in an extraordinary way. So
Thank you
thank
so
you
much.
so
Thank you
much,
so much.
Dr. Mahan.
Very kind of you. Thank you. Thank you. It was a pleasure for me. Yeah.
Thank you, Professor Mahan. And I just realized there's geometry all around me. That was a very interesting session. Thank you so much, Aisha, for your valuable time. Like I said earlier, it was a wonderful session, and I'm sure our audience too enjoyed being a part of the discussion as much as I did. We will be sending a recording of today's session via email to all registrations, and the video will also be available on Ashoka's YouTube channel. I would also request all our participants to take a minute to fill our feedback form so that we can constantly work on delivering excellent lectures. The link to the feedback form is in the chat box and will also be emailed to you. With this, we come to the end of season 3 of Scientifically Speaking. We hope to bring to you some fantastic sessions in the next season of Scientifically Speaking in a few months from now. Before we wrap up today, I would like to inform our audience that round 1 admissions to Ashoka University's undergraduate program will close tomorrow, 10th November 2021 at 11:59 p.m. Please note that you can secure your admission at Ashoka without your 12th board marks. Once again, thank you for joining today's session. If you have any further queries regarding today's session or would like to know more about Ashoka's unique interdisciplinary science programs, you can visit our website www.ashoka.edu.in or write to us at ugapply@ashoka.edu.in. You could also call us on our numbers shown on the screen. Thank you, take care, and stay safe.